this is 2017 EGMO problem number 5, and here is a view of this. Well, I think it's a number theory problem, right? We have this definition of an expansive n-tuple. N-tuple is an n-tuple of integers, not necessarily different integers, right? And if they satisfy this interesting property, and just to remind you, the left-hand side of this equality is a cyclic sum, as you can see here, right? And here there's a note about that as well. And the right-hand side, it is an odd power of 2. So given this definition of an expansive n-tuple, we want to answer these two questions. The first one is find all integers n for which this thing works. And for part B, given an integer m, can you make m a part of an n-tuple? So can you make it one of the terms? So as such, it is a different problem. So at first, it's not clear how, if they look like the same, but it's not. Well, I mean, for both problems, you need to have your hands dirty and start digging and see different applications. Obviously, n starts at 2, so let's check n equals 2. And then see if we can find a pattern after checking for 3, 4, 5, and so on. And ultimately, putting them together in a coherent way. Awesome, n is equal to 2, our product becomes a1, a2, a1 plus a2 I should say, a sub 2 plus a sub 1, we go back to 1. So that thing is supposed to, is it 2 to the power an odd integer? Well, obviously not, right? Why? Because the left-hand side is just a1 plus a2 squared. This is a perfect square I should say. And a perfect square is an even power, right? So not an odd power of a number, right? So for n equals 2, it's not gonna work. Let's try n equals 3. Okay, so we have a1 plus a2. So n equals 2 didn't work. Yeah, that one was bad. a1 plus a2, a2 plus a3, and then a3 goes back to a1. Again, let's check if we can write this as an odd power of 2. 2k minus 1 means it's an odd power of 2. We can, I guess there is, all it says about the AIs are they are different, distinct positive integers. They can't be negative, they can't be 0. Maybe we can try, all right, because on the right hand side you want a power of 2, each of these terms must be 2's, right? So I think that's clear, right? Because we are only allowed to use integers. Do you guys agree? So a1 plus a2, so for instance, if a1 I make it a 1, let's do a2 a 3 here. So 1 plus 3 is a 4, that's 2 squared, okay, fine. 3 plus, well, I already know plus 3, right? Do you guys agree? Sorry, that's a 1. Okay, a1 is a 1. Okay, all I need is to come up with an a3, which will make this as a product of 2, such that the power of 2 is odd. For instance, what happens if I do a 5? That's an 8, but this one won't be satisfied. What if 13 here? No. Actually, when I look at it, it's... Wait. Yeah, I can try 1. Yes, that's right. And, well, now let's count the 2's. This thing is equal to 2 squared times 2 squared times 2. Yes! It just did work, actually. Well, the question is, so how did we do it? Is there any rule, a particular rule? Or could we have done it simpler? Of course. Notice that we just realized here that 1 plus 1 is a 2. Why didn't we just did the other terms also 2? So instead, we could have used this one, 1 plus 1 times 1 plus 1 times 1 plus 1. That's just 2 cubed, and it's an odd power of 2. Perfect. It works. Indeed, because whenever n itself here is an odd number, because we have n factors on the left-hand side, if n is odd, then we have a product of an odd number of 2's, right? If we replace all the AIs. Okay, so I have a pretty good idea. If n is odd, then I think I can do it, right? So let's cut it chase. So 1 plus 1, 1 plus 1, just plug in oops, 1 plus 1, 1 plus 1. We have an odd number of these, n of them. N is odd, right? So odd number of them, and that's just equal to 2 to the n, right? Where n is odd, and boom, I'm done. Do you guys agree? So the solution n odd works. How does it work? For our expansive n tuple will be a1, a2, a sub n will just be made up of ones, basically. All right, let's go back to n equals 4, for instance. How about 4? Can we do it with n equals 4? Things are getting more complicated, right? Okay, so let's write that down first. A2 plus A3, and then finally A3 plus A4, and A4 goes back to A1, and I want to make it 2 to the power an odd number. For simplicity's sake, maybe I can replace A1 here with a 1 like I did earlier, but I still need to come up with some expressions here. Obviously, I can't do that 1, 1, 1 trick. If I do, then I will get 2 times 2 times 2 times 2. It's an even number, not gonna work. What if I do a 3 here, and then the rest is still 1s? Again, not gonna work, simply because this one, so we have a 4, 4, 2 4s, and now 2 2s, again, an even number of 2s. Not gonna work. So if one of them, okay, so if I were to make one of them 3, then I can try to bump it up to the next power of 2, which is, the next power of 2 would be 8, I guess. 4, so no, I don't want to use a 1 here, so let me add a 5 here. So that would give us an 8. I have a 5 here. Oops. Okay, so now let's check. So far I have an 2 plus 3, 5, an odd number of them. So all I need is an even number of 2s left, right? If I were to put a 1 here, that's, well, it won't work anyway. Yeah, I can try 3, for instance, right? So 3, that won't work, obviously. 3, 3. That would be an 8, that's a 4. Hey, I needed an even number. I mean, yeah, wait. I needed an even number here, and again, I have another odd number of 2s again, right? So 3 2s here, 2 more 2s here. It seems we have a roadblock here, right? So that's that obstacle seemed to be there. So yeah, you need to play with this a little bit more. And then you just realize that, hey, those roadblocks will be there. So there's no way out of these roadblocks. So we won't be able to find something which works actually in the even case. So far we did significant progress on part A. Well, kind of. Well, we know that n odd works, and we have a claim. Okay, let's do it. N odd works, and n even does not work. Does not work. We already have proven the first part, and this part is done, but this part is still there. I have not established this one yet, and because part of the reason is I don't have a nice framework yet to deal with this, at least visually appealing way to handle it yet. Awesome. So maybe we can directly go to the second part before I go back to the first part and finish part A. In part B, instead, we start naively with an odd positive integer, like m in this case. And if m is one of these numbers, it doesn't matter because it's cyclic product here, a sum product. One of them is m, then can we make that belong to an expansive set? Does that make sense? All right. So at this step, I want to clarify on one thing. Because we have a cyclic sum product here on the left-hand side, the best way to do it is probably a visual argument, right? So we're going to try to make the following. The name suggests it's cyclic, right? So I need to make a cycle, so this way life is better. We already have proven the case. Wait, did we prove n equals 3? Yeah, we did it. So we might try. So the next one we can try for m is m equals... Wait, no, we did... Well, okay, so we did it. Sorry, not that n, sorry. One of the terms should be 3. Do you guys agree? Whenever one of the terms is 3, we are done. So instead, what I will do is the following. Anytime I have something like this, and this is due to Evan Chen. So what I will do is I will express it in the following way. I will put my 3 here in the vertex of, because we have 3 numbers, I will just create a triangle basically, and I'll put my numbers on the 3 vertices. So I did use A2 is 3, A1 was 1, so let's just write it as well, and then A3 is also 1, right? That's it. 3, 1, 1. And then their sums, if you guys want, we can just put it on top of the edges. 4, 4, and 2, and boom. So all we need is the product of the numbers associated with the edges. 4 times 4, 16 times 2, 32 is 2 to the power 5, and odd, so that works. So from now on, I will just use this notation rather than doing this ugly product, sum product like that. I think that's reasonable. So we already did it for 3. 3 works. So can I make 5 the vertex of a cycle with enough 2's, with an odd number of 2's on the edges? And then we'll try 7 and then 9 and then see if we can get a particular pattern that will do our purpose. So n equals 5. So how can I construct it? So I start with a 5 and I want to go in. So I want to establish the 2 neighbors. Remember that if I have a 5, 5 will be involved at the beginning with another partner, and then it will have another partner in the end at the product, right? So that's why I have to go 2 sides. Well, what can I do? So somehow we want 5 to be a part of either. It should be a yeah. So how do I do it? Well, I think after you guys do a little bit of work, I think it's reasonable that because I want 5 plus something to be a power of 2, remember each term should be a power of 2, right? The sum. So whatever that number on that vertex is, when you add 5 to it, it should be a power of 2. And the simplest example I can think of is the next power of 2, which is 8 in this case. So if I put a vertex 3 here, I will get an 8 on that edge, and then I'll do the same thing on this one as well. So so this edge has a number 8, this edge has a number 8. So far we have 2 cubed here, 2 cubed here, so that's 2 to the 6, so not good. I can't just close the loop, right? If I close the loop, the product is, yeah, well, the product is not even a power of 2. This one's a 6. What am I thinking? Okay, ooh, terrible. Horrible turn of events. Horrible. Okay, let's go one more step. Well, why don't we just use the same trick that we have just did in just a minute ago, right? So I need to complete to the next guy, which is, if I add 1 to it, we will have 2 squared, which is, oops, not that one, this one. That will be a 4, that works. And I can do the same thing on the other side. Here's a 1, and then I associate it with the number 4. 3 plus 1 is a 4. Now let's count how many 2's so far. 2 2's here, 3 2's, another 3 2's, and then 2 more 2's. So far I have 10 2's, an even number of 2's. So actually now I can close the loop, right? So the cycle, we can just complete the cycle. Why? Because when I complete the cycle, I will get yet my very last 2. Okay, so sorry for that. Here, I'll get my very last 2. Do you guys agree this works? So now here in this cycle, I have 2 to the 11. That works. So that's why we didn't want it to finish it like this, if you will. Okay, come on. Oh yeah, so you didn't want it to have a quadrilateral for that reason, right? So I think that makes sense. If you had instead, we could have finished it like this, but this is not a good one. Why? Because you get an 8, 8, 4, 4, but here you have 3 2's, 3 more 2's, 6 2's so far, 4 more 2's, 10 2's. Not good. So this one has 10 2's, this one has 11 2's, so 2 to the power 11, and 11 is an odd number, so this one works. So n equals 5 works, but I just realized that I have to be careful. When I make an odd number work, I need to decide when to finish it. But I always have this flexibility. Do you guys agree? So I can always, anytime I need, I can make that thing here, that 1-1 trick. Do you guys agree the way that this trick works out? So if I will just stop at the convenient occasion. And by the way, I already knew this configuration would have worked and this one wouldn't work. Why? Because earlier we said that whenever n is odd, there's a solution. And I just realized that this one has an even length anyway. So therefore, this configuration would no way would have worked. So therefore, yeah, I'm not surprised to see this one works actually. Okay, let's try 7 as well. And then maybe we can, it's time to write out what we have, right? In the case of 7, I'm guessing it will work out like this, right? So you have a 7. And then let's do the same thing. So let's complete it to the next power of 2. So therefore, this one is an 8. If you want, I can just count the number of 2's in it, right? So I can say 2 cubed here, 2 cubed here. Okay, so far I have 6 2's. We can... Wait, I can just complete the cycle. That would have worked. But what's wrong with it? Well, what's wrong with it is, what about the rule? We need to create a rule. I can't keep trying every single n forever, right? Okay, even if this works, I don't want to do it this way, right? So keep working on it. So I want to keep extending it. But how much more? Like how long? Let's do it based on our rule, right? So what was the rule saying? The rule was saying earlier, how did I do it? I started with 7, go to the next power. Actually, this would have worked. That's also what our rule says. So, yeah. Okay. So that was, all right. So the rule says on the edge, make an power of 2 such that it will be next, right? The next power of 2, which is more than 7, right? The smallest power of 2, which is more than 7. So what is the smallest power of 2, which is more than 1? And that's a 2. And there will be a 2 here as well. You guys agree? And to make them 2's here, I need to add the vertices as 1 and 1. Do you guys agree? The sum of the vertices is the edge, right? So that's kind of the idea we are suggesting here. Okay, so at this stage, how about completing it like this? This would work, right? So I have 3 plus 3, 6, 7, 8, 9 2's. Or alternatively, we could have directly completed the loop right here. Anytime you have 2 1's next to each other, just complete the loop. So it doesn't make sense to continue the way I did here. So, okay, so obviously when you write out the proof, you need to explain it. But suddenly, that also gives me a very cool idea. And the idea is the following. Implicitly, I gained insight into how I can approach this first part of the problem. Look at how I just kind of reduced it to a smaller case. Instead of a 5-vertex shape, we reduced it into a 3-vertex shape. And that kind of gives me an idea that maybe I can use an inductive argument to prove the first part, that even numbers won't work. All right, so and that's pretty much it. So for whenever you have a number, now we know exactly how to deal with it. Okay, let me show one more example so that everybody's clear how we're doing it, and then you describe it with your own words pretty much. So all we do is we construct this polygon, and the next vertex will be such that the sum would be a power of the smallest power of 2 greater than the number in the middle, right? And then we keep going. So the next one would be probably a 1 here. That would be 2 cubed. Another 1 here. That would be 2 cubed. Would it have made sense to just finish the polygon like this as a quadrilateral? No, because if you did that, that would have been a 2 cubed as well. It wouldn't have closed. The loop wouldn't have closed. But instead, now we can close it. Why? Because now we have an odd number. So in the previous case, if we closed it like this, that would have been an even number of 2's, not good. So now, though, we have an odd number of them. 3 plus 3, 6, 9, 12, 13. Yes! 2 to the power at odd number works. And that's it. I can always do this. When I do that, so the closing, so the way we close it, so we need to particularly explain how the closing happens, and each time we should be able to close, right? The reason is, actually, the more I think about it, I think we can have a very good argument for that. Okay, so for part B of the problem, so each time you start with the desired number m, so n equals m, right? So the question is asking for m, odd. So whenever you start with m, go to the next vertices such that the edge, so whatever those vertices are, VV, they are the same number, obviously, by the construction, by our algorithm. Our algorithm says, just write this 2 to the power, the power of 2, such that 2 to the k is the smallest. And it is still greater than m. But because m is more than 2 to the k minus 1, right? So such that 2 to the k such that 2 to the k is strictly greater than m, yet 2 to the k minus 1 is less than m. M is odd, so as a result, it's either m. So do you guys agree? So whenever so you find that k which will do this which will satisfy this condition. Once you have the k, you keep going on. But suddenly it makes a huge observation, and the observation is this. What can you say about the magnitude of v? This one is also 2 to the k. Well, I claim v, note, v is less than m. Do you guys see why? Because this one is 2 to the k, and because m is greater than 2 to the k minus 1, it is clear that 2 to the k minus 1 is half of 2 to the k. So v, because m plus v is equal to 2 to the k, and m itself is greater than 2 to the k minus 1, it must be, so therefore this implies v is strictly less than 2 to the k minus 1, meaning v is less than m. Perfect. But if that's the case, that's an infinite descent, right? You start with a positive integer. You can't keep doing this forever. Ultimately, as you do your descent, and let me descent over here. That's terrible. Okay. Just watched Angry Birds. Terrible. Horrible turn of events. Okay. The next guy will be, I don't know, v prime. This sequence can't go forever, right? I don't know. We can call it v double prime. Ultimately, we will reach 1 on both ends. Do you guys agree? But because the two branches, they have the same number of 2s, so far we have used an even number of 2s. Finally, the moment you reach the 1, you can connect them and you have your remaining 2 here. Done. Yeah, that would solve part B. But then, like we said, we can go back to part A, and now we can finish the part A simply using induction. So anytime, so we already have proven this, that an odd works. All we need now is to show that an even would not work. And yeah, you can try a couple of examples and you would see the following, right? So let's, oh gosh, I wrote too much already. Okay. So an even does not work. Claim. Proof. Well, there's different ways you can prove it. You can either do an extremal argument and use infinite descent again on this case. That would work. Or if you want, you can do the which case? The induction as well. Either way you call it, whatever you call it, it's kind of similar argument where it's kind of like a recursive argument in that sense. But the main idea is the following. We already established n equals 2 does not work. For obvious reasons. We said that whenever it's 2, you get a perfect square. Already we said that. So when n is equal to 4 and 6 and 8, so what I can do is the following. Let's check the case n equals 4, for instance. If you have, or maybe I should write it the same way we did it earlier, like this. Suppose that we have this situation here where, I don't know, I'm just making up some numbers here. Maybe I can put a 3 here, a 1, a 1, a 1. How about that? We need to establish that's bad, right? So that can't work. So the way we will do it is, obviously what you can do is, because one of them will be the largest, so suppose that this guy is the largest one. It will have 2 neighbors, right? So it will have 2 neighbors, and because this guy is largest, yeah, when you look at the largest one, which is 3, the largest vertex 3, what's kind of surprising is that the 2 numbers on the edges, the powers of 2 on the 2 edges, are both equal to each other. Do you guys see that? Well, this is no coincidence. For the largest guy, because he's the largest one, the 2 neighbors will be smaller than that, and yeah, so these numbers would have to be equal to each other. Yeah, otherwise this guy wouldn't have been the largest guy after all, right? So does that make sense? Because there's only 1 power of 2 that we can add, so that like we can rise up to, and that's 4. If we were to rise up to 8 here, then this guy would have been a 5, and this will contradict the maximality of this guy. But anyhow, noticing that 3 is the maximum, the 2 next to it are both, the 2 edges have both 4 and 4 here. And as such, because it's an even number, we can totally ignore them, because all we care is, so there are 2 2's here, 2 2's here, so 4 2's, an even number of 2's. In the grand scheme, it's just totally ignored, and all we care is for the rest of them to have to have an odd number of 2's. So basically, once we ignore this top portion, the problem is, or if you will, we just ignore 2 of these vertices. So we short circuit this guy over here, like this edge onto here. But wait, earlier we said that if you have a cycle like this, 1 plus 1, 1 plus 1, you will never, regardless of what these numbers, they don't even have to be 1. They can be any 2 numbers. This will always be a perfect square. Perfect square is not acceptable. We want an odd number of a 2, right? So this is not good. So that gives us the idea for the inductive argument. So the inductive argument basically will start with so basically we can start the inductive argument in the following way. So suppose that you have this cycle, this big cycle. Obviously this cycle will contain the largest guy, I don't know, whatever it is, let's say here. Then because this guy is the largest, the 2 neighbors to that guy, they have to be equal. So whatever is the edge total here, 2 to the k, this guy has to be 2 to the k as well. Is everyone clear on that? I hope you guys can see why this is the case. If these 2 edges are the same, then it means these 2 are the same as well. Let's call this v and v. They have to be the same number. But then, like we did earlier by an inductive argument, we can just remove these 2 and we can directly connect this vertex to this vertex. And so the problem reduces. Now we will check again in that reduced form with 2 less vertices. See, we have now n minus 2 vertices where n is an even number, right? So check for the same argument, check for the largest element. The 2 neighbors of that largest element has got to be equal to each other. And well, just for those of you who didn't see it, so if this guy is the largest, what will be the power of 2 here? If it is not the smallest power of 2, which is bigger than m, if you don't use the smallest one, then you will end up using, then it turns out that one of them will be bigger than m itself. Just as an example, so I think, yeah, the explanation is not that good, I think. So what I'm saying is, suppose that this guy is a 13, and so you put a 3 here, and so that's 2 to the 4, which is good. So if you don't want a 2 to the 4 here, you need to at least bump it to 2 to the 5. But 2 to the 5 would mean that 32, you would have to put a 19 here. Aha. So, but this contradicts the maximality of 13. So we started the argument with, okay, we have an n gone, where n is an even number. And then you find out which one is the largest vertex. Here the vertices represent the AIs, obviously. And then from there we establish that the 2 neighbors of that vertex has got to be equal. Such a case won't happen, right? And then, so this way we should inductively reduce the number of edges by 2 each time. And ultimately it will reduce all the way to the base case of 2, but earlier we have established that the base case of 2 won't work because you get a perfect square. A1 plus A2 times A2 plus A1 is just A1 plus A2 squared, which is definitely not an odd power of 2 in the right hand side. So that's it. That solves this really nice. What is this problem? Is it a combo problem? I think it feels like a combo problem as well, right? So I don't know whatever the nature of this problem, but yeah, so that solves this really nice problem.